Hi everyone, so in this video we're going to take another look at Coulomb's law. And from a prior video, you might recall that Coulomb's law describes the force of attraction between two charged particles by the proportionality constant K multiplied by Q1 and Q2, which are the charges of the two particles in question, and then d squared, which is the distance of separation of the Q1 and the Q2. So in this case, for this very nice diagram by Klein and Dutro in the mineralogy textbook, on this vertical axis in all three of these panels, instead of force per se, they're looking at minerals or compounds where they're comparing melting points. So the melting points here are a proxy for the force of attraction. And in this top panel, they show sodium as it is bonded to fluorine, chlorine, bromine, and iodine. Now, if you take a look at your periodic chart, fluorine is up at the top and iodine is down at the bottom. This is the smallest of the anions and this is the largest. So if we take a sodium atom and we bond it to the smaller fluorine atom, we get a very small distance between the center of those two atoms. But if sodium is bonded to a much larger iodine atom, then the distance is much greater. With a greater distance, we would get a weaker force. So the way that is translated here is that this smaller distance here and the stronger force translates to a higher melting point for the compound sodium fluoride, whereas the greater distance for sodium iodide leads to a weaker force, which translates to a much lower melting point. The neat thing about this, by the way, is that the Q1 and Q2 are effectively constant. The only thing that's being changed in this diagram is the distance due to the different sizes of these atoms. All of the Q's in this case are a +1 for sodium and a -1 for either fluorine, chlorine, bromine, or iodine. So the only thing that's changing in this equation is this distance, d squared. In the second diagram here, the second panel, we have a parallel situation where we have oxygen and it's being bonded to magnesium and calcium, strontium, and barium. And all of these have a 2+ charge, and the oxygen has a 2- charge. So we've changed the magnitude of these charges here in this equation, but those magnitudes in this diagram here are going to be the same, and it's only the distance that's going to change because we're going to increase from the very small magnesium to the much larger barium. And where the distances are small, the interatomic distances, we get a high melting point, and where they're larger, we get a lower melting point. And then this final diagram down here, it's parallel to the top one. So sodium is being bonded to fluorine, and then we have potassium fluoride. We also have lithium fluoride, and then rubidium fluoride. So everything's being bonded to a similar type of anion. Actually, it's more analogous to the second panel here. I think I said it was analogous to the first. It's really closer to this guy. So we have different size cations. They are all of a +1 charge, and all of these fluorine atoms are a -1 charge. So again, this top part in the Coulomb's law is being held constant. It's only the d that's changing. And again, where the distance is small, you get a high melting point. Where the distance is large, you get a low melting point, except for lithium fluoride. Lithium fluoride, as they show, has the smallest interatomic distance, as you can see here, just 2.07 angstroms. So its melting point should be way up here if it were following the curve. So it's a little bit of an exception. This Coulomb's law is not only being affected by this kind of attractive force, but if the atoms themselves are very, very small, like lithium and fluorine, if the cation itself is very small, then there's not a lot of space in between the lithium atoms. And so when we start setting up an array of atoms, there is a negative force. We can have a Q2 and Q2. We could rewrite the Coulomb's law here, where we're looking at the force of repulsion between a Q2 fluorine and another Q2, well, we could maybe, well, I don't know if we really want to use the same number. We will here. And then in this case, we'd have a repulsive force because we have a minus charge here and a minus charge here. Maybe formally we'd want to change the notation, but for our purposes, if this distance is very small and the fluorine atoms in the structure start seeing one another, then we have this negative repulsive charge, and that might weaken the structure and cause a lower melting point, a lower Coulombic force for lithium fluoride than what we would predict from this simple projection of that dashed line.